page 3 of discrete random variables. So think back to the investigation where we talked about a multiple choice exam. That is a good example of a binomial distribution. What are the things about that that make it binomial? First of all, think about the word binomial. Binomial means there's two different outcomes, okay? So you can't say, oh, what's the probability you get A? What's the probability you get B? What's the probability you get C, etc.? That would be more than one outcome. But if you classify it into right answer, wrong answer, then it becomes two outcomes. So it's a two outcome experiment. The other thing is that you repeat the same experiment multiple times. So like every single question is a repetition of a simple experiment, a two outcome experiment. And then finally, every time you do the experiment, every time you do the repetition, it has to be the same condition. So it always has to be the same probability. So number one, it has to be repeated. Number two, two outcomes. Number three, same probability every time. Okay, so let's analyze these four cases here and decide whether they're a binomial distribution. And if they are a binomial distribution, we're going to write it in this form, which is that capital X is a binomial distribution, and it has n repetitions, and it has a probability of p each time. Okay, and if it cannot, state why. Okay, so a fair die is numbered 1, 2, 3, 4, and is thrown 7 times. Find the probability that an even number is obtained exactly 3 times. So sounds repeated, yes. Two outcomes. Well, a die, when you roll it, can have 4 different numbers, but they classify it into 2 different cases, which is even number, odd number. So that means it is binomial because they grouped it into 2 different cases. And then finally, it's the same probability every time. Yes, because every time you're just checking to see if it's even, which would be half the numbers, right? So if we wanted to write it in terms of that format, we would put capital X is a binomial distribution, and the number of repetitions is 7 because they repeat 7 times, and the probability each time is even number in 4 numbers. That would be 2 out of 4. Okay, you could put 0.5 too. All right, B. A box contains 6 green dice, 3 red dice, and 3 white dice. A die is selected at random from the box. The die's color is noted and is not replaced. This experiment is repeated 4 times. Find the probability that the green die is selected fewer than 3 times. Okay, the key word here is not replaced. Whenever you don't have a replacement, think back to when we did probability and probability trees. If you don't replace the dice each time, then that means that the probability that you get that colored dice next time is going to be different. So the probability is not going to be the same each time, which violates the third condition that we have the same probability each time. So no, it can't be binomial, and the reason why is because it's not replaced. Not replaced means that we are going to have different p each time. Okay? C. A dice is selected at random from the same box, its color is noted, and the dice is replaced. This experiment is repeated 4 times. Find the probability the green die is selected fewer than 3 times. Okay, so in this case, we do replace it, so the probability is the same every time, so that's good. Maybe there's multiple colors, but they're only classifying it into 2 conditions. One is that a green die is selected, and the other is that another color is selected. So it's binomial. That's 2 outcomes. That's good. So it's the same probability, and it's repeated. So it looks good. So I'm going to put that it's a capital X is, instead of saying capital X, you could say the random variable X is binomial distributed. And how many repetitions? There are 4 repetitions, 4 times. And then what's the probability? The probability is that the probability that the green die is selected fewer than 3 times. What you're going to put here is the probability that you get the green die. Let me see. Oh, I think they're talking about this. Okay, they're talking about this box here. So 6 green, 3 red, and 3 white. What's the probability that you get green? It will be 6 in 6 plus 3 plus 3, 6 and 12. So it would be 0.5 also. Okay, and then you actually don't use this information that, oh, what's the probability that the green die is selected fewer than 3 times? This tells you you're supposed to use binomial CDF instead of binomial PDF. but it doesn't really enter into your decision of whether or not this is a binomial distribution, right? So the only part that you really need to analyze if it's a binomial distribution is how many times do you repeat the experiment? Are the conditions for success and failure defined in two possibilities, like green die or not green die, and also that it's the same each time, which means that the die is replaced. Okay, the fact that you're looking for fewer than 3 times selecting the green die gives you the X variable that's in binomial CDF, but it's not necessary to declare that this is a binomial distribution. Jasmine is packing her bag for a 4-day music festival. The weather forecast for each of the days states that the probability of rain is a constant value of 30%. Find the probability that will rain on at least 2 of the 4 days. Okay, once again, raining on at least 2 of the 4 days, that's not really important to decide whether or not it's a binomial distribution. This is only important to decide if you're going to use binomial CDF or binomial PDF. And in both of those cases, it is a binomial distribution. Is it repeated? Yeah, 4 days. So it looks like it's going to be n equals 4. Is the probability the same each day? Yeah, it looks like it's 0.3. And are there 2 outcomes? Yes, rain or no. So I'm going to write it out that the binomial or the random variable X is binomially distributed, and there's 4 days of the music festival. So it's the experiment repeats 4 times, and the probability is 0.3. So and that's all we need to know. The rest of it is only important when you actually calculate the probability. Okay. All right, let's move on to number 3. Silk scarf in a factory. Quality control investigations find that 0.5% of the scarves produced have flaws which reduce their value. A sample of 30 scarves is selected from the factory. Calculate the probability that the scarf has exactly 1 flawed scarf. Okay, so in this case, our n value is 30, right? And our p-value is 0.5%. If we change that to decimal, we have to move the decimal place 2 to the left, so we get 0.005 as our p-value. And then we want to know the probability of exactly 1 flawed scarf, so that would be x equals 1. We do need to use what, PDF or CDF in this case? Well, exactly, that gives it away. We should use PDF for this one. Okay, so we're going to do second distribution, binomial PDF, which is option A, and we're going to type in the n value of 30 scarves, p value of 0.005. What's the probability of it being a fail, being a defective scarf, and 1, what are we looking for? We're looking for 1 defective scarf or flawed scarf out of 30. And the probability is, the probability is 0.1297, or if you round it to 3 significant figures, it would be 0.130. What about the probability of no flawed scarf? So that would be equivalent to x equals 0. So then we go to second distribution, option A again, because it's exactly 0. So put 30, 0.005, exactly 0 flawed scarves, and that'll be 0.860. Okay, so a really good chance that there are no flawed scarves out of 30. What about 1 flawed scarf or less? There's 2 ways you can do this. One is you could take 0.860 and add it to 0.130 because 1 flawed scarf or less is the probability that x is equal to 0 or x is equal to 1. You could also express it as the probability that x is less than or equal to 1, right? So you could add 0.860 to 0.130, or you could do binomial PDF and put x equals 1. So let's do that. Binomial CDF, because binomial CDF works with less than or equal to. So we're going to put, oops, wrong ones. Let's get out of that. Second distribution, and we're going to go to binomial CDF. And we're going to put 30. And we're going to put 0.005. And we're going to put 1. And this should give us 0.860 plus 0.130. It's 0.990. Okay. Last of all, one flawed scarf or more. So one flawed scarf or more is actually, we can't do this with the calculator because PDF does the case where it says exactly. CDF does the case where you do less than or equal to. There's no calculator option which does greater than or equal to. So you need to reframe the greater than or equal to cases as 1 minus the probability of a less than or equal to case. So the probability that x is greater than or equal to 1 is equal to the 1 minus the probability that x is less than or equal to 0. Like what is, the opposite of greater than or equal to 1. And we already know that the probability that x is less than or equal to 0 is the same as this probability. Okay, so it's actually 1 minus 0.860, which is equal to 0.1396. Okay, or if you were rounding, 0.140. Okay. Number 5, a weather station in a remote area is powered by 10 solar panels which operate independently of each other. The manufacturer states that each solar panel has a probability of failure of 0.085 in any given week. The weather station needs at least 6 of the solar panels to be working in order to function. A, find the probability that no panels failed during the week. So our n value is that we have 10 solar panels. The p value is the chance of failure is 0.085. And in this case, the probability that no panels fail would be x equals 0, right? So second distribution, we're going to go to a PDF because we're talking about exactly x equals 0, not... Actually, in the case of 0, you could do CDF or PDF because less than or equal to 0 is the same thing as is equal to 0, right? So I could put 10 here. 0.085 here, and the x value I'm going to put 0, and it's 0.411. Oh, I'm sorry, 0.411. Okay, next one says find the probability that 3 panels or less failed during the week. This time, are we going to use CDF or PDF? Well, it's 3 panels or less, which will be x is less than or equal to 3, right? So we're going to use binomial PDF or CDF because it's less than or equal to. And then we're going to put 10 solar panels, 0.085 chance of failure, and 3 or less. And the answer is 0.993. So the probability that 3 panels or less fail during a week is 0.993. It's pretty good. Find the probability that 4 panels or more fail during the week. So that would be x is greater than or equal to 4. Remember, the calculator cannot calculate the greater than or equal to scenario. So you need to reframe it as 1 minus the probability of a less than or equal to scenario. So the probability as x is greater than or equal to 4 is equal to 1 minus the probability that x is less than or equal to 3, which means you do 1 minus, and we already found the probability that x is less than or equal to 3. We found out that it's 0.993. So we're going to do 1 minus 0.993, which is 0.00721. 0.00721. D, for the weather station to stop working, how many solar panels need to fail? So at least 6 need to be working for it to function. So that means as long as only 4 are broken, then it's okay. So how many weather panels would need to break for it to stop working? It would need to be 5, right? 5 need to fail. Okay, so what is the probability that it fails? So that would be the probability that the failures is greater than or equal to 5. And remember, we can't do a greater than or equal to problem on the calculator. We need to reframe it as a less than or equal to problem. So it'd be 1 minus the probability that x is less than or equal to 4, right? Because if x is greater than or equal to 5, that's the opposite of x is less than or equal to 4, okay? And we haven't found x is less than or equal to 4 yet, right? So let's find it. So the probability that x is less than or equal to 4, we could do that with CDF with x equal to 4, right? So we'll do that. We'll go second distribution. And we'll put 10.085 and we'll put 4. And the answer is 0.9992. So the answer is, really small, 0.000777, 0.0007757. Okay. If you were going to write in scientific notation, you would write 7.76 times 10 to the negative 4th. Okay. Okay, so that was E, and that we're done with the page.